Hi everyone. Today we will continue discussing our topics in induction motor. So in the last session, we discussed together the equivalent circuit, just to remind you about the equivalent circuit again. So the equivalent circuit of the induction motor, we have stator circuit, we have rotor circuit. So the stator circuit is nothing but the primary circuit of the transformer. So R1 is the stator winding resistance. X1 is the leakage reactance of the stator winding, and again, it's a function of F1. RC is the equivalent core resistance, and XM is the magnetization reactance of our core. E1 is the induced volt from the stator side, and here are the definitions. For the rotor circuit, let me clean all of these. Firstly, for the rotor circuit, guys, so for the rotor circuit, we agreed that we made like an equivalent for the rotor circuit. So during motion, we know that because we have frequency for the rotor circuit, which is F2, and F2 equals SF1. So we replaced all parameter that depends on F1, F2 by S times F1. So in this case, you would have S times X2, you would have S times E2, and we made a relation to release the S expression from the induced volt and from the reactance as well, in order to make it all as a function of F1 and reach to like practical circuit for our motor. So we said that I equals E or SE to divide R2 plus S or J SX2, and we divided over S in both numerator and denominator, so we end up with E2 divide R2 divide S plus JX2. So this is again no prime. Still we are working in the primary, in the same side. We didn't make referral yet. So this is now the equivalent circuit we have. So we have here the leakage reactance and the resistance as a function of slab. The next step we made, that we released also the slab from the resistance in order to have the physical resistance value. So here we have R2, we have X2. So all elements now are like exact physical values we have. And here we end up with that we have another term here as a function of the machine operation, which is R2 divide S times 1 minus S. Now, this is a rotor circuit. Let's mix both of circuits together. So mixing both of circuits together means we have to refer one side to another, because now we have magnetic core like what we have in transformer. We have primary side and secondary side. So we have here also stator side and rotor side. So we would use the turns ratio between stator and rotor in order to do that. So as you can see here, you will get the values already referred. So it's not the turns ratio is not giving. Okay, and this is going to be the case in all of our questions. So the equivalent circuit will be given as referred to the stator side. So it's not like transformer. You will have a lot of cases you can transfer between primary and secondary. No, in the induction motor, all the examples or questions, you will find that all parameters are referred to the stator side. Okay, so the turns ratio will not appear with you in the numerical examples, but here just to know the idea how we made the referral. So by the end, this was the stator. This is the rotor. What happened? E1 of the stator is the same as A, which is the turns ratio, times E2. So we refer now the rotor circuit to the stator circuit. So this would be multiplied times A, which is N1 divide N2, or N stator divide N rotor. So A is nothing but the turns ratio, which is N stator divide N rotor. And again, N here means number of turns. It's not speed. Okay, so this is stator number of turns, this is rotor number of turns. And the same is for the reactance. So we would have now X2 prime, which is the leakage reactance of the rotor circuit referred to the stator circuit. And we would have R2 prime, which is the rotor resistance referred to the stator side. Okay, guys? And we would use the same ratio. So R2 prime equals A squared times R2, like what we made here also for the reactance. Okay, the same is also for that term. So R2 prime divide S is nothing but A squared times R2 time divide S. Okay, so again, guys, I'd like to uh, give some more details about this point here. Take care that R2 is a physical resistance. X2 or R2 prime, X2 prime, these are physical elements. X2 is leakage reactance. Okay, leakage reactance can be determined experimentally, but R2 prime or rotor resistance can be measured by ohm meter. The term R2 prime divide S times 1 minus S, this is a virtual element. It's not exact element or physical element you can measure. However, you can calculate for sure. And this depends on the motor operation. Now, we have here a term called PAG. What is PAG? Actually, this is related to the power flow, and we will discuss today the power flow of the induction motor and go more in deep in the discussion about the power in the induction motor. So let's see together the power flow. Power flow, the input power. So this is for motoring mode, guys. So we will focus on the motoring operation right now. The input power is AC power. So it's like any three-phase AC power now, which is root 3 times V line times I lines times cosine theta, which is the power factor. VT, again, is line volt. IL is line current. Cosine theta is power factor. So these are the terms of the input power. Let me draw the equivalent circuit here in order to, or let me copy the equivalent circuit from the other slide right here. So as you can see, guys, when the input power, AC power, comes to the motor, a first thing that we will see is the stator copper resistance. The stator resistance. So we would have stator copper loss, PSCL, stator copper loss. So this is a first loss that we will have. Any copper loss, guys, is nothing but I square R. So based on the equivalent circuit here, we can say it's going to be now 3 times I1 square times R1. So this is going to be P copper 1. So P copper 1 is stator copper loss. Then we would have some losses across the core resistance. So this is going to be called core loss. Core loss, as you know, guys, core loss is going to be constant. We consider core loss to be constant all of the time, even when we practically identify these values or experimentally identify these values, we get these values and consider this value constant because it depends on the supply volt. Someone can say, the volt across the RC is not the same as the supply volt. Yeah, this is correct. However, the voltage drop across this impedance is very small and can be neglected compared to the voltages between V1 and the V across the core resistance. So we can consider that the core loss is constant and the value is going to be V1 squared divide RC. Okay, so this is the core loss of the induction machine. Now, since the power is going to flow from the stator side to the rotor side, we have here what's called air gap power. So the air gap power, if you would like to calculate the P air gap now, so I can say P air gap equals Pn, the input electrical power, minus P copper 1 minus P core. Correct? So this is the P air gap right now. The P air gap means the power transferred from the stator side to the rotor side. Once this power enters the rotor side, we have a physical resistance, which is R2 prime. So we would have rotor copper loss. And again, any copper loss is nothing but I square R. So we can say that P copper 2, so P copper 2 is referring to the rotor copper loss. This is equal 3 times I2 prime square times R2 prime. So this is now the rotor copper loss. The remaining power will be converted to mechanical power. One can say, hold on, we still have another resistance here. Why you didn't say that we have some copper loss across this resistance? The answer is this resistance is not a physical resistance. And we mentioned that in this session and previous session. So there is no physical resistance called R2 prime times 1 minus S divided S. This is not a resistance that we can measure by ohm meter. So we don't have copper loss here. But we will represent this term for a certain power, but it's not loss. It's going to be gained power because this is going to be happen due to the motor operation. So the power across R2 prime is a loss power. However, the power calculated for this term R2 prime divide S times 1 minus S is a gained power. It's not losses. So by the end of rotor copper loss, this is going to be power that will be converted now to mechanical power. I can say, since the remaining power that will be converted to the mechanical power, this can be represented actually using this term. So I'm going to say this is P converted because this is the last element that's available in our circuit now, and this is the remaining power that will be converted to mechanical. So I can say the converted power or the mechanical power equals this term times I square. So I can say the P converted now equals 3 times I 2 prime square times R 2 prime divide S times 1 minus S. So this term now represents a gained power, the converted power, which is the mechanical power we will obtain from our machine. Since this is mechanical gained power, we would have some mechanical losses like friction and stray loss. So friction loss is the torque friction times omega. So this is torque friction times omega motor. And the gained power here is going to be induced torque times omega. Okay. So by the stray losses, a constant value will be given in numerical examples. If not, we can neglect the stray loss. And the remaining power is going to be the output power, which is load torque times omega m. Now we have the expression of omega m. Omega m is nothing but the 2 pi divide 60 times the speed in RPM. Okay, so this is nothing but the radian per second representation of the motor or rotor speed. What about omega s? Where is the omega s in this case? So since this is induced torque, which means electrical torque, can we have another relation for air gap power as a function of the induced torque? Yes, we can. So we didn't have any kind of relation now for the air gap power as a function of parameter. We just get the air gap now as a function of input and other losses. But we need to get P air gap relation as a function of the machine parameters, as we made now for the converted power. So the converted power as a function of the machine parameters, this is a value electrically, and this is a value mechanically. So let's see, guys, the other relations we have. So here, the P air gap. So we agree that P air gap now is the power that will be remaining from the after deducting the loss of the stator. So we can say that P air gap now depends on the terms of power that will be dissipated in this part. We have some losses, we have some gained power. So the summation of the power from that side is going to be the P air gap power. So we can say now it's nothing but R2 prime plus R2 prime divide S times 1 minus S. So the summation of these two terms times the I2 prime square. And you remember that R2 prime plus R2 prime times S, divide S times 1 minus S. So the summation of this part is nothing but R2 prime divide S. So we can say that P air gap equals I square times R2 divide S. Take care that here it's not referred to referred to stator side. If it is referred to stator side, so this is going to be in and also multiply times 3 for the three phases. So all of these relations here, guys, are considered for per unit or per phase. So in order to get these actual values, you have to multiply times 3. So we can say now P air gap for three phase equals 3 times I2 prime square times R2 prime divide S. So this is the air gap power as a function of the machine parameters. What about the mechanical? Mechanical wise, or mechanical relation, we can say it's equals to the induced torque, which is the electrical torque, times omega S, the synchronous speed. Why the synchronous speed? Because it's still in the air gap. Still, the air gap power is the flux air gap power between stator and rotor, and this motion is depending on the synchronous speed. So the P air gap can be considered as the induced torque times synchronous speed in radian per second. So this is the P air gap. And as we discussed, the P mechanical is 3, it should be also 3 for three phase, I square R2 divide S times 1 minus S. If you compare that to P air gap, so we can say it's 1 minus S times P air gap. Please, guys, don't be confused between having the relation for three phase or for per unit, because this is the relation for any multi-phase induction machine. So we just multiply times the number of phases. Okay, so and you would find that in all of books of the electrical machines. So this is a per phase model. So for three phase, just multiply times 3. So P mechanical again equals I square R2 divide S times 1 minus S. If you refer that to the primary side, or let's say, sorry, stator side, so I2 prime square times R2 prime divide S times 1 minus S. If you compare that to P air gap, again, it would be 1 minus S times P air gap. If you compare P copper 2 to the air gap loss, sorry, to the air gap power, you would find that P2 or P copper 2 equals S times P air gap. So we have now P mechanical or converted equals 1 minus S times P air gap. And we have P copper 2 rotor copper loss is S times P air gap. So we can make this relation, guys. P air gap to P2, which is P copper 2, to P mechanical equals 1 to S to 1 minus S. And you can use this relation anytime, which means you can get P copper 2 from P mechanical, not only from P air gap. How it comes? I can say simply that if you divide these two relations here, so I can say P mechanical divide P copper 2 equals 1 minus S divide S. And P air gap will be omitted from the from the two divided relations, which means you can use it from here. P mechanical divide P2 equals 1 minus S divide S. So you can memorize this relation to get any missing power from these terms. Okay, so this is one interesting thing about the relation of powers in the induction machine. Let's solve a numerical question for the power flow of the induction machine here, guys. So this example says three-phase, 15 horsepower, 460 volt, 4 poles, 60 hertz induction motor. 1728 RPM. So I'd like to write down all notes from the nameplate data we have here. So 15 horsepower is nothing but P out. So P out at rated condition equals 15 horsepower, which is, if you like to convert that to kilowatt, so it's going to be 15 times 0.746 kilowatts. And 460 volt, so this means the line to line volt. What is the machine connection here? It's not mentioned. If it is not mentioned, by the way, you can assume that the machine is Y connected. Okay, so this is one common connection. We use it mostly for the induction machine. So assume that it's Y. This doesn't mean that we have delta connection induction machine. We have also delta connection. But I mean, if the example or the numerical question did not identify the connection, so you can assume the Y connection, and it's going to be more easy for you to assume the Y connection. Okay, because you just need to get the phase volt from the line volt. However, all other currents are going to be the same. So Y connection, we can assume it's Y connection. So we can say now V1 phase equals 460 volt divide root 3. 4 poles, so number of poles equals 4. 60 hertz, so frequency F1 equals 60 hertz. 1728 RPM. Which speed is this one? For sure, guys, we do not have such number as a synchronous speed, because synchronous speed is depending on frequency and number of poles, and no way to have like fraction for the number of poles or frequency different to 60 or 50. So no way to have this number for a synchronous speed. So this has to be here the uh, uh, rotor speed. So this is the N rotor. So I'm gonna give it a name of NR, or rotor speed, equals 1728 RPM. But again, rotor speed is going to be variable. It depends on the operating condition. So we can say that this is in rotor at rated value. So this is a rated speed. Then 1728 RPM induction motor delivers full output power to a load connected to its shaft. So this means this machine is going to work at full load. Full load means rated value. So this means the value of the rated speed here you can use, and the value of output power at rated also can be used. The windage and the friction loss of the motor is 750 watt. So this is the windage and friction loss. So we can say that P friction equals 750 watt. Determine the machine power developed, and then the air gap power and the rotor copper loss. I'm gonna solve that with you here, and by the end we will compare that to the textbook numbers. So start firstly with the mechanical power developed. So mechanical power developed is P mechanical, which is equal to P converted, guys, correct? So the relation of this one is 3 times I2 prime square times R2 prime times 1 minus S divide S, and this is also equals 1 minus S times P air gap. This is from the electrical equations. From mechanical equation, we can say this is torque induced times omega m. So these are all the relations for P mechanical. How can we get the P mechanical right now? What is given and can be used in order to get that P mechanical? If you see that here, he mentioned the power or the machine is working at full load. So we have the value of P out. So can we say that P mechanical from the power flow equals P output plus P friction and windage loss? So this is going to be now P out, which is 15 times 0.746 kilowatt plus the power here, which is 750 watts. So since this is in kilowatt, so let's say the other term also in kilowatts, so 0.75 kilowatt. And from here we can get the value of the mechanical power. So let me calculate that with you. 15 times 0.746 plus 0.75. So this is 11.94 kilowatt. So 11.94 kilowatt. Okay, so this is a mechanical converted power. Now, so I'm gonna say this is A. B, the air gap power. So the air gap power, P air gap, I'm gonna write all relations as well. So it's nothing but 3 I2 prime square R2 prime divide S, which is equal also to induced torque times omega S. And as a function of the other relations, so we can say it's equals to P mechanical plus P copper 2. And you remember that we have another relation between the three terms of power, P copper 2, P mechanical, and P air gap. And I'm going to write this relation here. So P mechanical divide P air gap equals 1 minus S. divide 1. So this is a relation. So I can say from here, P air gap equals P mechanical divide 1 minus S. Correct? So I can say this is P mechanical divide 1 minus S. So we already calculated the P mechanical. What is the value of slip here in this question? So simply, we can calculate the slip because we have the rotor speed at full load, and we know the frequency and number of poles, which means we can calculate our synchronous speed. Actually, even without calculation, we know that the standard for 4 poles, 60 hertz machine, the synchronous speed is going to be 1800. So this is 1800 RPM synchronous speed. We know that. So we can say now S equals 1800 minus 1728 divide 1800 and calculate our slip. If you do this calculation, let me do that on my calculator. So 1800 minus 1728 divide 1800. So the value is 0.04. So S here equals 0.04. So we can substitute now in this relation here to calculate the P mechanical. So sorry, the P air gap. So 11.94 divides 1 minus 0.04. So this would give us the value of the air gap power. So 11.94 divide 1 minus 0.04. So the result is 12.435 kilowatt. So this is the air gap power. Third thing is, what is the rotor copper loss? So rotor copper loss, you know that we can say now P copper 2, which is rotor copper loss, is nothing but S times P air gap. So this is 0.04 times the S of the air gap, which is 12.4375, or you can say P air gap minus P mechanical. So it's the same. So this is now equals 0.4975 kilowatts. So 0.4975 kilowatt. So this is the solution, guys, of this question. Let's compare to the numbers we have from the textbook solution. So as you can see here, 0.4975, 4975. So this is in watt, this is in kilowatts. So all the numbers are the same. So I'm gonna copy the solution of the textbook on another slide to keep this here for you. Okay. Let's see these MCQ questions, guys, multiple choice questions. So the induction motor speed is the induction motor speed. So the induction motor speed firstly is nothing but the NR, our rotor speed, correct? So this is NR. So this speed is greater than the synchronous speed, equals the synchronous speed, less than the synchronous speed. Take care here, guys. I said the induction motor. And according to our discussion for the time being, we didn't discuss generator yet. So for the motor operation, all of the time the NR is less than the synchronous speed. Does it mean in generator the rotor speed is higher than the synchronous speed? Yes, this is correct. So for induction generator, the rotor speed is going to be higher than the synchronous speed. Okay, and this is one of the major differences between induction and induction motor and induction generator. So once you increase the motor speed over the synchronous speed. So the power flow is going to be reversed and the machine is going to work as a generator. And by the way, this is one way to start the operation of induction generator in the power plants. You know that? We mentioned before, in order to generate electricity from induction machine, you have to have a source of flux. And we mentioned that we have two ways to make a source of flux. A first way is self-excited induction generator using some capacitors to build up the flux in the machine, or using the slip ring type induction machine and supply the rotor by field. So this is called doubly fed induction generator. However, still one way is to have a squirrel cage machine. You can start the generator firstly as a motor. So if you supply three-phase AC to the machine with the same operation as a motor, so the speed is going to be less than the synchronous speed. However, if you insert the prime mover power after that to continue rotating the machine in the same direction and increase this speed, the machine power flow will be reversed and can work as a generator. So this is one way we use, guys, in industry to make or start the induction generator in power plants. But we have to provide supply firstly to drive the induction machine as a motor. Okay, nice. And this is an easy way, by the way, to make the start of the induction generator without having self-excited type or capacitors. Okay. The second question is, the advantage of the induction motor is it needs single supply compared to synchronous one. It has lower weight compared to synchronous motor. It has higher efficiency compared to synchronous motor. Cheaper than synchronous motor. Now, guys, I have a philosophy in the multiple choice questions, so we can have more than right answer. Okay, so here, for instance, we will have more than right answer, but I'm gonna comment on all the choices we have in order to understand the concept more in deep. So, firstly, I agree, and I think all of you also agree that it needs single supply compared to synchronous motor. So synchronous motor needs two supplies, one for the field winding and one for the armature winding. But here, induction motor needs just one supply. So this answer is correct. It has lower weight compared to synchronous motors. Here we need to stop. The synchronous motor has field winding across the rotor and dumper winding across the rotor to start the motor. So if we compare the rotor of the synchronous motor compared to the rotor of the induction motor, you will find that the synchronous motor is higher weight. Again, now we have, for synchronous motor, we have rotor windings and rotor core. For the induction motor, we have also rotor winding, or let's say the squirrel cage. We have the rotor core and the cage winding. But for synchronous motor, in order to self-start the synchronous motor, if we have the damper one, so in this case, the weight of the machine, of the synchronous machine, is going to be higher. And stator-wise, both synchronous and induction machine with the same rating will have the same stator core and windings. So we can say it has lower weight compared to synchronous motor. This is correct. So I'm gonna say this is also a correct answer. Again, guys, why? So I said stator-wise is the same. Rotor-wise, in the induction machine, we have the squirrel cage. In the synchronous machine, we have the rotor core plus the rotor winding plus the cage. So synchronous motor is more heavy compared to the induction motor. Okay, so this is one thing. Another thing, you still have for the synchronous machine, you still have the brushes in order to supply the field winding after that. So definitely synchronous motor is more heavy compared to the induction motor. The third thing here, it has higher efficiency compared to synchronous motor. Actually, this is incorrect. Why? You remember, guys, we mentioned even this in the synchronous machine discussion. Did we discuss copper loss in the synchronous machine? We did not discuss copper loss in the synchronous machine. Copper loss in the rotor winding. Why? Because the rotor winding is gonna rotate with the same speed of the stator flux. But here, in the induction machine, the motor is rotating with less speed. Otherwise, according to the operating rule or the way of the operation of the induction machine, if the rotor speed became equal to the synchronous speed, the machine will slow down and stop. But it will not stop because, again, once the machine is slowing down, there will be a difference and it will speed up again. So what I would like to say is the rotor all of the time will rotate in average speed less than the stator flux. And this will create copper loss in the rotor of the induction machine. And we could see that in our power flow diagram and calculations. So copper loss in rotor is there. So efficiency wise, the synchronous motor is more efficient than the induction motor. Okay, so I can say this is incorrect. Last thing is, it's cheaper than synchronous motor. Yes, I agree, 100% agree, because let's say, guys, the cost depends on many factors in industry. One of the factors for sure is the mass production. So if you have something exist a lot in industry with a mass production, so this means it's gonna be cheaper than the other product. However, if you neglect the mass production and start comparing the machine construction itself, you will find that rotor is just a piece of rotor circuit is just a piece of iron, sorry, a piece of copper, just the cage. You don't have windings, you don't have a lot of complicated manufacturing process to make the rotor like what we have in synchronous machine. Stator wise, we said synchronous and induction are the same. But let's compare just rotor. So the squirrel cage induction machine is much cheaper than, or let's say the squirrel cage rotor. Squirrel cage rotor is much cheaper than the synchronous machine rotor. So this makes the synchronous machine is more expensive than the induction machine. One more thing is you don't have any kind of connection to the rotor circuit in induction machine. However, you have in synchronous machine. So this makes extra cost for the synchronous machine rotor circuit. So definitely, yeah, the induction machine is cheaper than the synchronous motor, or let's say motor, not machine. So induction motor is cheaper than synchronous motor with the same rating. And let's say this is for the squirrel cage type. If you go to the slip ring type, it may be relatively complicated and costly as well. However, we do not use slip ring a lot in industry like the squirrel cage. Slip ring can be used or most probably used with very high power okay, more than 300 or 250 horsepower machines. And this is not because of the machine itself, but because of the how the power electronic is going to be expensive for the squirrel cage for this rating. So we can use slip ring with different controls instead of the AC drives. So we may use conventional drives like adding resistance for the speed control. And later on, we'll discuss more about the speed control of the induction motor and understand the meaning of adding resistance to the slip ring induction motor to control the motor speed. So this is now the concept. So I agree here that we have three correct answers in this question. So, and this is the way, guys, in any exam, please, for any multiple choice question, you have to understand every choice. And you can have more than one correct answer in the choice. The last question, and we will end up with this question today. The rotor losses of the high rating synchronous motor. The rotor losses of the high rating synchronous motor. Higher than that of induction motor, can be neglected compared with induction motors, very high due to high value of cutting speeds. Again, let's analyze every choice. Firstly, what copper loss we would have in synchronous machine. So you know that for the rotor, we supply the rotor by DC. And we remember that the field circuit of the synchronous motor will absorb very small amount of current compared to the stator windings. So for the high rating machines, if I'm gonna say, for instance, I have a machine of like 15 megavolt ampere, I may find that the field winding is several kilowatts, which can be neglected for sure compared to the stator power. So for that high rating machine, the rotor copper loss will be higher than that of induction motor? No, it's gonna be less than, for sure. Why? Because we just mentioned that the machine will rotate with the synchronous speed, which means the cutting speed is zero. So we don't have reaction coming from the stator side to make losses on the rotor circuit. So first choice is incorrect. The second choice can be neglected compared with induction motors. I agree. This can be neglected because the induction motor will have huge copper loss actually compared to the synchronous motor. A third thing is very high. So from the first point here, guys, very high, this is incorrect. So I can say this is incorrect, but let's continue reading the sentence. Very high due to the high value of cutting speed. Actually, the cutting speed in the synchronous machine equals zero because cutting speed is nothing but the difference between stator current speed or rotating flux of the stator speed, okay? Or let me rephrase the expression again. The speed of the rotating flux of the stator, because the stator is stationary part, okay? Compared to the rotor speed. So for synchronous machine, the flux in the air gap rotates with ns, synchronous speed, and the rotor rotates also with ns, which means cutting speed now is zero. But for induction motor, it's different. And this is the main concept of the induction motor operation. So here, I can say here the third choice is incorrect. So the correct one is gonna be the second one, okay? So please, guys, follow this strategy when solving the multiple choice. You will have some conceptual questions in the exams. So please analyze the question as per our discussion here in order to understand the concept and getting the correct answer. So for these materials, guys, we covered these materials in the previous session and this session. We learned the following: the construction of the induction machines. So we discussed the stator, the rotor types, the different rotor topologies of induction machine. We discussed the slip ring and the squirrel cage. The operation of the three-phase induction machine. We discussed the operation and how the flux is built and the machine is speeding up, and how the machine, when reached to synchronous speed, it will slow down and work in the average between two limits or 2 points in order to have constant speed. And we drive together the equivalent circuit of the three-phase induction motor, and we discuss the power flow of the three-phase induction motor. In the next session, we will go more in deep and discuss more approximated equivalent circuit for the induction motor in order to analyze the performance and the mathematical model of the induction machine. Thank you so much, guys, and see you in the next session.